You've probably heard of a capacitor before, but did you know that inverters have capacitors inside of them? They're actually a very important part of the inverter because they smooth the voltage on the DC bus so you don't get a ton of ripple as the inverter is chopping up the power to make it into AC waveforms. I have here a small 100 volt, 100 microfarad capacitor, and I've charged it to about 50 volts. If I touch the wires together, you see a little bit of a spark there, and that's with this capacitor only filled to about half of its voltage rating. Now, imagine in this inverter, we have this big old bank of capacitors. Let me get you a close-up on this. This is the actual inverter board out of one of the Quattro 10K inverters I have here on the right, and this is just absolutely loaded full of 80 volt, 3900 microfarad capacitors. There's about 22 on top and even more of them down on this board down below. So there is an absolute boatload of energy stored in these capacitors when the inverter's charged up. Now that's all fine and good while the inverter's operating. However, this inverter's sitting here right now with no battery connected and the capacitors are empty. Let's say I just plugged in these connectors so the inverter was connected to the battery and flipped the breaker on. Well, the same rush of current that can come out of a capacitor can also go into that capacitor. So what I have here is a 48 volt lithium iron phosphate battery, and this battery can dump a ton of current inrush into that inverter. And if it went unlimited, it could damage not only the battery, but also the inverter. So how do we handle that? A common way is to leave one of the wires disconnected from the battery with the breaker off. Make your final connections throughout your system, turn on your switches, and then before you put in the last connection, you turn on the battery and you use a resistor. In this case, I'm using 10 watt, 10 ohm resistor, and you connect it in series before making your final connection, and this slowly charges up the capacitors in the inverter, so that way when we make this final connection, there's no big spark. That's all fine and good if you're experienced, but there's one problem. It's very dangerous if you've made a mistake with your system. Let me give you an example. Let's say you have a short circuit. In this case, I have this Anderson connector that is literally a short circuit. Let's say you plug that in, and that simulates a mistake in your system, and then you take your resistor, and in this case, I'm going to use vice grips here or channel locks to hold the connection, because this is going to get really hot here. Let's say you take this pre-charge resistor and put it across a short circuit. You see that spark? Well, this is also getting really hot and starting to smoke, and it's frying the resistor. If you were holding, ooh, that smells bad. If you were holding this in your hand, it would definitely burn your hand. Let's get a close-up shot again of what that looks like if you have a short circuit with that resistor. You can see a little bit of a spark, and now smoke is coming out of that resistor as it gets really hot. And this is sure stinking up my, my test bench area here. So the way I recommend pre-charging is once you've made all of your connections, when you're getting ready to make your last connection, you grab a light bulb rated at the same voltage of the system. So this is a 48 volt light bulb. This is actually the headlight for a forklift. If I get you an up close here, you can see this is a 48 volt, 40 watt light bulb. There's 2 pins on the bottom, and that just slips into this base here like that. And now I have my positive and negative wires. So now instead of using the resistor, I'm going to take the light bulb, turn the battery on, and since it's an incandescent light bulb, it acts like a resistor, except if there's a short, it's not going to burn up and melt, it'll just light up. So as you can see here, I'm pre-charging the inverter through the light bulb. As it fills up and the voltage goes up, as you can see on the meter, the light bulb gets dim. And then once I reach about 50 volts, I'm ready to go. The inverter's charged up. So now I can take the light bulb out of the circuit and make my final connection safely with the inverter capacitor staying charged up and no big spark when I connect the terminals, damage to the BMS, or damage to the inverter itself. Now, since we're talking about safety here, you may be wondering, how is this any different if there's a short circuit? So if I put my cable back that simulates a short circuit, all that happens in the event of a short circuit is the light bulb lights up. So as you can see here, if I go across the battery, It just glows bright and never goes dim, and that's the dead giveaway that there is a short circuit in the system instead of it going bang and blowing up in your face like it would if I made the connection right now. So the moral of the story is, if you want to be a little bit safer when you're pre-charging the capacitors on the inverter, use a light bulb instead of a resistor. And I'll do it one more time. You can see the light bulb glows bright as it's got the highest difference in potential. And as that voltage of the inverter goes up, you can see the light bulb gets dim. And then once you see the light bulb goes out, at that point, it's safe to put the terminal on the battery and tighten your screw down.